Okay, welcome to Aerodynamics 1, I believe. My name is Rich Hewitt. I'll be chairing the next hour. Our first speaker is Peng Cheng Kwan from University of Manchester.
Right. Good afternoon, everyone. My name is Peng from Manchester University, and it's my pleasure to be here to share some of my work did last year. And this project is to reduce the flow separation using Hellborn Ribonase in supersonic speed. So the contents of my presentation will be introduction, flow facility, and channel model, experimental methods, baseline case, and the control effectiveness of the Hellborn Ribonase and control mechanism, and finally a brief conclusion. Right, so introduction. So shockwave boundary layer exists almost everywhere on a high-speed flight vehicle. And when the shockwave is strong enough, the boundary layer could be separated. And because of the separation, it could lead to a lot of detrimental effects to the performance of the aircraft, such as the wind, the buffets on winds, the pressure loss in inlets. So normally, people will want to reduce the flow separation using a lot of flow control methods. However, active control methods such as plasma actuators, magnetic actuators, they are still along with from being applied to practical aircraft. And passive control methods such as control pumps and water generators, they tend to be more useful in transonic conditions and less useful in supersonic. And additionally, they can also induce a lot of parasitic drag. So new flow control methods are still being sought by a lot of researchers, and which can induce as low as possible drag while still being useful in supersonic. So Hellborn Ribonase is what we used in this study. And this is kind of a bio-inspired control method originally used for drag reduction in low-speed flows, but recent research has also shown that this kind of convergent, divergent surface roughness can induce large-scale vortex structures in the boundary layer. So the flow facility. All the tests were conducted in the high-speed supersonic tunnel in the University of Manchester at a total pressure of 7.4 bar, total temperature of 65 degrees, and Mach number of 5, and the unit Reynolds number is 17.6 million. So this is the model tested. So basically, it has 3 surfaces, and around this corner, the boundary layer will be separated here, and the Ribonase were applied from the leading edge, and this is some of the parameters of the Ribonase, and they were laser manufactured on a very thin film. With the thickness of the film is 110 micron, and this lowercase h is the depth of the Ribonase. 6 cases were tested. So case 1 was the baseline case, and case 2 was tested with a small strip, just strip without any Ribonase. And case 3 and 4 were tested with Hellborn Ribonase with different depth. And case 5 and 6 were tested with either stream-wide Ribonase or span-wide Ribonase with the same depth as in case 4, 78. Schneering was used to visualize the shockwave boundary layer. PSP was used to measure the surface pressure and estimate the size of the separation area. And TSP was used to measure the surface heat flux. So, so the flow for the baseline case. So this is the surface pressure, and this is the surface heat flux. So both of these 2 parameters follow the similar trend. So they stay a lower value on the first surface, and then get higher on the second surface, and then lower again on this flat surface. And so in order to assess the control effects of the Hellborn Ribonase, we need to find out a way to define what the separation really is. And so in this study, we use this surface pressure and heat flux. So separation point in this study was defined where this pressure starts to rise here, and the attachment point P2 was defined as where the Hay flux gets to its peak value. So the separation length would be the distance between these 2 points. And I know this deflation is not 100% to the accurate separation length, but essentially it should be proportional to the real separation length. So we use this criterion for all the cases to assess the separation length. So this is the new result for case 1 to case 4. So around this corner, you can see in case 1, the separation shock is quite clear, and it doesn't change too much in case 2 with only small strips. And in case 3, when Herborn Ribnitz were applied, the shock wave is kind of weaker, and when the depth gets bigger, in case 4, this shock wave disappears. So we can see from here that it kind of reduced the separation. And this is the surface pressure distribution for case 1 to 4. So as I mentioned before, so the separation area should be somewhere indicated by the light green area around the corner. So from case 1 to case 4, so without control, the separation area should be something like that. And in case 2 with small strips, the separation area is corrugated. And in case 3 and 4, this size of it is reduced substantially, especially in case 4. And also from the surface Hay flux, we can see that some Hay flux structures can be observed existing in pairs behind each of the strip. And we assume these are the footprint of the counter-rotating vortex structures induced by the Herborn Ribnitz. So the separation length for case 1 to case 4 can be calculated by the criterion I just talked about. So from case 1 to case 4, so the separation length should be from 16, 9, 7, and 4 mil. So it gets smaller and smaller with the control of Ribnitz. Right, so control mechanism. So some of you might think that since the boundary layer of this case is lambda, so some of you might think that the separation is only reduced because of the translation and not because of the counter-rotating vortex structures. And so in order to exclude the effects of translation, we did 2 more sets. So in case 5, this one, the Ribnitz were aligned streamwisely, and in case 6, the Ribnitz were aligned span-wisely. And so both of the Ribnitz in case 5 and 6 were the same depth as in case 4. So as you can see, only in case 4 can the separation area be reduced substantially. And in case 5 and 6, you can only see some random turbulent wedge features here, and not this counter-rotating vortex structures here as in case 4. So we assume that transition is not the dominant mechanism of the reduction of the separation in this case. So brief conclusion. So we see that Herborn Ribnitz can be used to reduce the flow separation, and it can induce large-scale vortex structures in the boundary layer. So it is the counter-rotating vortex induced by the Ribnitz that help reduce the flow separation. And that's it. Thank you.
Time for a question or two? Yep.
I may have missed it, but what was the height of your reference in comparison to boundary layer thickness?
So the boundary layer thickness at the end of the Ribnitz should be about 0.45 mil, and the thickness of the Ribnitz is 0.78. No, it's 78 micron, so 0.078.
Okay, let's thank our speaker and move on to number 7.
Okay, so good afternoon, everyone. Thank you all for coming along.
My name is Alex Gillespie, and I'm here from University of Southampton. And today I'm just going to be giving you a brief overview of some of the work that I've been doing in the first year of my PhD. So the main area of research that I'm going to be looking at is shock boundary layer interactions, and specifically large-scale simulations of interaction of oblique shock wave with turbulent boundary layers in the context of internal 3D ducts. And in recent years, there's been a kind of growing interest in the influence of sidewalls on these kind of interactions in the flow structure. So that's also what I'm going to be looking at, along with the kind of influence of shock strength as well. So just to give you some context, this was a study that was done a number of years ago, a numerical study from Southampton, looking at basically the effect of sidewalls on the flow structure. So the flow here is coming in, supersonic flow from left to right, and we have a shock generator here, which is imposing an interaction on the bottom surface and associated flow separation. And by varying the aspect ratio, basically they were able to see that the sidewalls do have quite a strong influence over both the shock structure as well as the separation sizes and things like that. And another sort of aspect of the project looking at shock strength, and this is another numerical project which was just looking at basically increasing the flow deflection angle in order to trigger a Mach reflection. So in classical aerodynamics, this problem is quite well understood, but there isn't actually a lot of literature in this area of real flows. And so in this example, we have a Mach 2 flow, and going from 12.5 degrees to 14 degrees, they're able to trigger a Mach reflection there. But this case was not considering sidewalls at all, so it was a completely periodic condition in the span direction. But we do think that there is an influence of the sidewalls on this as well. So this is a wind tunnel project done at Imperial, which by basically keeping the same flow deflection angle and the same Mach number, they're able to trigger a Mach reflection just by varying the height of the tunnel. And so by effectively increasing the aspect ratio, that you do get a transition there to Mach reflection. And so piecing all these sort of three things together, we think there is a lot of work to be done that can sort of determine what combination of these of flow deflection and sidewalls contributes to Mach reflections. So because this is a numerical project, obviously you need a solver. At Southampton, we have a solver which deals with a kind of niche area, which is architecture flexibility. So there's a growing need basically to use various architectures. So whether you're working on CPUs or GPUs or both, it is handy to be able to be flexible without having to rewrite a lot of your code. And that's what our solver helps with. We have a Python front end where you define your whole problem, your numerical formulation, your equations and whatnot. And that is then converted into OPSC code, which is basically a generic form of parallel codes, which then could be targeted towards whatever specific architecture you want. So one day you could be working on CUDA on GPUs, or on the next day you could be working just on CPU cores with MPI. So that's kind of the main strength of our solver. So what I'm going to be focused on mostly is the problem of inflow generation. So in common across all turbulent studies, numerical studies, you do need to generate a turbulent boundary layer upstream of whatever interaction you're going to be looking at. And so the method that we have combines a mean profile and a fluctuating profile. So the mean profile we generate with an analytical method using the input Mach number and the Reynolds number. And we combine this with a fluctuating profile, which is done in two parts. So first we have this unscaled fluctuations, which is basically a correlated field of random numbers, which I'll get to in a moment. And this is then scaled to the right Reynolds number distribution, so that the size of the fluctuations, the intensity of the fluctuations resembles a real turbulent boundary layer. So the the unscaled fluctuations we are generating with this method by Kim, which is sort of built on a number of other methods, but the underlying one is this method by Klein, which I think some people might be familiar with. But basically, this is an iterative method where where we assume that there's an exponential 2-point correlation in the turbulent structures. So there's 3 parts to it. So in the y direction, we iterate along the grid in y, and we combine, to find the correlation at the next step, we combine the current step in accordance with this exponential law, and then a random number contributing the rest of it, basically. And in principle, this is then repeated in the z direction, and then again in the streamwise direction. And that gives you a full plane of filtered fluctuations, which can then be scaled and then added to your mean profile. And the key input here is your integral length scales. And so that by basically prescribing those, it means that the turbulent structure can have basically the correct shape. So just to sort of give you an idea of how this is applied, in principle, it's a fairly simple method where you basically iterate from one point to the next, where one point contributes to the next, and it sort of builds up, so you get the structures across the grid. And so for a sequential code, it's relatively straightforward. But in a parallel code, your grid might be decomposed into something like this. And it's especially bad for GPUs where the grid is decomposed into much smaller blocks. And so because these are all solved in parallel, you have the problem where you need this result before before it's actually calculated. And so basically what we've worked on is how to deal with this. And the approach that we've taken is to, instead of using the points from the current time step, we take the points from the previous time step at t minus 1. And so because these results are basically pre-calculated, there's no issue with the parallelization. And so, so there's no issue applying it there to different architectures. And this makes, it's basically, is assumed that between data planes there isn't as much variation than there is along the grid points. So the convection step is much smaller than the grid stepping, as well as the integral length scales in the streamwise direction are longer. So on paper, it at least looks like it should work, but you obviously have to verify that it does. And so this is just applying the method to a Python code which does the whole method, and then which basically generates thousands of planes of inflow data, which can then be time averaged. And what we find is that it collapses back to the target data that we scaled our fluctuations with, which is good news. Basically, that's exactly what we're looking for, and that suggests that the method is not losing any of the original mathematical proof of the original method. So then the next step is to verify that this does actually produce a turbulent boundary layer. And so this is applying it with OpenSPLI on a Kepler P100 GPU. So it's fully parallel at Mach 2.7, which is kind of the target Mach number that we're going to be looking at. And so these are just basically just isosurfaces of density. And you can see that from the inflow here carrying through, the turbulent fluctuations are sustaining, and it's developing into a physical boundary layer. This might give you quite a good idea of how the method is working. This is just streamwise velocity contours very close to the bottom wall. And so the inflow is here. And so close to the inflow, you have basically unphysical fluctuations. So it might resemble a turbulent boundary layer in some ways, but it's entirely unphysical. But this allows us to develop real physical structures downstream. So we're fairly happy that this is actually sustaining a turbulent boundary layer. even though it's been decomposed into a parallel grid. So what's next is basically just to extend this, extend the grid up to around 15 boundary layer thicknesses. This will allow us to basically determine at what point does it become a properly physical boundary layer, and basically the earliest point that we can start using it for interactions. And so once we have that, we can then apply it to the sort of main scope of the PhD, which is looking at different flow deflection angles, different shock strengths, and various aspect ratios. We can then investigate sort of the main sort of hypothesis of the PhD. So I think that's all I have time for. Thank you.
Time for a quick question? Yep.
I just wonder, the inflow generation method you described, how would you modify them if you have sidewalls? Or how would you plan?
Yeah, so the mean profile, you can generate the mean profile for the main sort of areas of the walls, and then you just have to deal with the corners in that case. And so you basically, you blend the mean profiles effectively. The same sort of idea is applied to the fluctuations. So you have one filtered data field, but what you do is you vary the integral length scales in accordance to where it is in the wall, near the wall. So whether it's sort of on one wall or when it's the corner, you basically just vary the length scales there, and then you can you can then blend the amplitudes of the fluctuations as well. Yeah, so you basically just have to handle each bit by itself. But in principle, it's definitely doable.
Okay, thank you.
All right, thank you.
Hi, my name's Oliver Taylor. I've come from Imperial College, and I'm here to talk to you today about the effects of surface roughness on boundary layer transition on a blunt body in hypersonic flow. So, hypersonic aerodynamics, what is it? What's special about it? Well, generally, above Mach 5, certain phenomena become sort of quite significant, particularly surface temperature and heat flux. And here's a nice picture of something that you might see that's sort of hypersonic vehicle in 10, 15 years' time, maybe. So a bit about the context. So I mentioned you get very high surface heat transfers. So this is some experiments that I've done. What we're looking at is a blunt body in a otherwise hypersonic flow. You can see I've circled there. We've got two little roughness elements. Just remember those for later. And then for a bit of context, a number of heat transfer gauges positioned here and here. So that's what I've just said. If we just have a video, this is sort of, it's an actual experiment. What we're looking at, this is tunnel runtime. Pressure ramps up at the start. You get a bit of steady runtime about now. It lasts for about 6 milliseconds. Doesn't seem much, but it's plenty. And then you get the slow ramp down. I don't think you can quite see it. So here, I focused in, and you can just about see two very faint lines just here. And these are shocks off our roughness elements. So our roughness elements are very thin. You can't see them on the schlimm, you can't see them on anything, but you can obviously see they have a physical effect on the flow. So boundary layer transition is important. You can see up to an order of magnitude increase in heat transfer between the laminar and turbulent boundary layers. So it's driven by surface roughness quite often. These are two experiments that I've done earlier, and this top one is for a large element, and the bottom one is for a small element, and also some smooth models. And you can see that, in this, I think you've got about 5 times increase. Depending on your configuration, it can be a lot greater. And these are all measured downstream on the model with elements up by the nose. So I've mentioned you've got large elements or small elements. But what happens if you have something in between? So what I'm focusing on here is the heat transfer profile of a single element with intermediate thickness. And you can see what you get. You get these intermittent turbulent spots. So these are short patches of turbulent flow in an otherwise laminar boundary layer. And so that's for one element, but then you never have one element in isolation. You might have rivets, you might have roughness, it might be due to the structure of the material. So what happens when you add a second element? So these are all configurations where I've added a second element at small span-wise spacings. And if you go from the bottom, you've got two elements touching to the top where there's 6 widths between the elements. And if you look, they're not all the same. So when they're wide, you get a lot more turbulent spots. Okay, you've got 2 roughness elements here, you might expect that. But then the interesting one I want to bring your attention to is this one here, when the spacing's small but not quite touching, where you almost seem to get very different behavior. So this study, what is it? Well, so all those earlier bits are from experimental studies. I'm now going to focus on a bit of numerical stuff I've done to actually try and understand what's causing these phenomena to occur. So it's a numerical study where I've not matched the whole configuration, but I've locally tried to match the conditions. So you've got whilst the model's in a Mach 9 tunnel, the actual boundary layer edge velocity is about Mach 2.4. And so I've simulated on a flat plate a number of these little roughness elements. And it gives results. So this is for when the spacing's quite wide. So it's almost an element in isolation. And you can see you've got 2 pairs of vortices. You've got a bit of a trailing edge vortex pair in the center. You've got horseshoe vortex, which sort of forms around the outside. And these give rise to streaks in the boundary layer. And I'll talk about those more a bit later, but you can see here you've got sort of a high velocity streak, a low velocity streak in the center of the flow, and another high velocity streak. And so what do we see? Well, this is when we start looking at 2 elements together. And actually, it's not just one element in isolation anymore. You can see that the flows actually interact. Leave that to play a second. And yeah, so you can see the different vortices forming downstream. You can also see some shock structures and other bits in the flow. So about these streaks. So the amplitude of these streaks is an important factor in transition. It drives the shear layer in the boundary layer. Actually, the greater the amplitude of the streak, generally the faster the instabilities occur. There's an Anderson paper back from 2001 which characterizes it this way. It's basically the difference from your mean boundary layer flow. And then these are some of my experiments for some of my computations. So what I've got this for a number of different spacings. You can see wide spacings, it's sort of fairly consistent. Small spacings does something funny, but then where we got that drop in the number of turbulent spots we saw in our experiments, you can also see there's a decrease in the the amplitude of the velocity streaks. And so if I focus on this one here, which is I've just taken it at 1 downstream position, you can quite clearly see there's a definite minimum there. So why does this happen? Oh, sorry. So I'll just go on to this bit first. This is a transient solution that we've got. Had a look at the spectra, see if we could identify the physical features that were occurring. This is a contour plot showing the frequency spectra at different points across the boundary, across the width. And we can actually see sort of main features. So you can see so this mode here would generally assume is associated with the vortex shedding mode from the roughness element. And this one here, about 0.05, appears to be the first mode in the boundary layer. But then when we bring the elements close together, things start getting a lot more complicated. So whilst we can see the bits of the vortex shedding and maybe a little bit of the first mode in the boundary layer, you also get a lot more seeming to happen in our flow. So what is this? Well, it started looking at the shedding modes. So picked out a single mode and plotted contours of pressure. And so if you look at this video here, this is for when the elements are wide. You can see it's quite uniform across the flow. It's symmetric about the center. But then when you bring 2 elements close together and plot it at the top, you can see that this actually breaks down and the the shedding mode actually sort of changes frequency very slightly on the inside, so the plane of symmetry seems to have a slightly lower frequency in comparison to the outside. So what causes these bits? So I've got sort of two main effects I want to talk about. Firstly, the pressure. So again, talking about one wide, one narrow configuration. So when they're wide, you've got these, they look independent. You get a region of high pressure to the front of an element, and you get a region of low pressure at the back. And these thicken the boundary layer, which forces your vortices higher up, and so actually creates a higher shear. When they're close together, though, you no longer get two independent regions. You get this one sort of combined region, which actually has a greater effect on the thickness of the boundary layer. And the second one is a sort of a geometric effect. So when you're bringing these two elements close together, you sort of, this is a sort of a plot of the centers of their vortices. And they appear to sort of concertina together. So when they are very narrow, you do get the trailing edge vortex, which is the dominant one in terms of forming your low-speed streak. And these do seem to go up and be more damaging, essentially pull more low-velocity fluid up into the flow. And so to just summarize up, I've done some experiments that revealed this suppressed transition for intermediate spacings. I've then tried to characterize this using a numerical study. Found that the wake is a function of the spacing, and for small spacings, the vortex shedding does seem to change. I've then had a look at the amplitude of the velocity streaks, which seems to be a critical factor and does explain the delayed transition. And they also appear to be a function of the pressure changes and the vortex position. And then the drop in the amplitude of the streaks does explain the delayed transition. Thank you.
Quick question?
So the boundary layer thickness is from CFD, numerical studies done, just laminar reference. Sorry? So not in the experiments, no.
Yep.
Have you got any plans to try and experimentally validate your conclusion of your CFD? So why is this happening?
So part of experimentally, what we're trying to look at, what the next plan is to actually come up with these configurations, and we've used the same logic to take it a bit further and see if we can actually position the elements to try and create a new minimum. And the plan is to, stick those back on the model and try and take some heat transfer measurements. But that's the plan.
So, good afternoon, everyone. I'm Tom Fisher, and I'm going to talk to you about the work we've been doing to develop background-oriented Schlieren in hypersonic flow. And this is presented with work that's been done by myself, my supervisors Mark Quinn and Kate Smith, and this is funded under the European Space Agency under an MPI scheme. So, first of all, why do we care about this? Well, optical Schlieren, which is the established technique, requires good optical access. And if you've got a wind tunnel, specifically a transonic wind tunnel, you don't really have very good optical access. Often, you have limited views. The optics themselves are expensive. It's very difficult to set up. So if you're a lab student and you're crawling around trying to align lots of different mirrors and everything all over the place, it's a real pain. And if you try and do more complex stuff, the complexity and the time just goes absolutely through the roof. There's scale limitations, so there's a finite size you can make your mirrors. And these are the real physical elements which set the spatial sensitivity of your system. You cannot really do this on an in-flight vehicle, so can BOSS provide a possible solution? So the aims of this study, as part of the wider study of my PhD, I'm evaluating optical techniques for compressible flow. So that is conventional optical Schlieren, which I'll just call Schlieren from here on in, and background-oriented Schlieren, which I'll call BOSS. To do this in a steady-state case, I've been using a flared cone model. So this generates a complex flow field, gives you lots of different flow features which you'll typically see in compressible flows. So it's a good analogy for what you might want to do to develop the technique. So multiple features, evaluate the spatial sensitivity. and I'm evaluating the parameters affecting the sensitivity of the two techniques. So free stream static density, which is common to both BOSS and Schlieren. So when I do the actual test, we change the static density values. And then the things which are unique to BOSS, which are the processing algorithms, the background patterns, and throw distances. So again, we've got a variety of different things that we're going to look at to examine it. So in terms of density gradient techniques themselves, the images along the bottom basically go in terms of complexity of setting up the technique. So density gradient methods, they exploit the refractive index change that you have when you have compressible media. So this is great for compressible flows because we can look at it without having to put stuff in there and disrupting the flow. Primarily they're qualitative methods, so things like Shadowgraph and Schlieren, which are the first two images, are really good at showing you what's happening around your model. If you want to start to gain more information, so you want to start to quantify, say, the density field, then that puts you into doing things like color Schlieren, which is the third image of Concorde, or an interferogram, which is the final image. And these are just through the roof in terms of optical complexity and setting up. So rather than putting the pressure on the user to do this, why don't you put it on the computer? Because we have advances in image processing technology, so maybe we can leverage that to improve what we can do. So on the image now, on this screen now, this is an image of the flared cone model that's been tested at the university's hypersonic wind tunnel. So we can do Mach numbers of 4, 5, and 6 for around 7 seconds, as my colleague Peng explained earlier. As you can see, we've got a variety of different flow features. So we have a conical shock, we have some separations, reattachments. So in this image, we have quite a variety of different sensitivities we're trying to pick up. And this provides a challenge for Schlieren. So if you want to pick out one thing in particular, you're going to have to tune your system. Then you're having to sacrifice picking up one feature for the sake of another. So you have to do more run times already. In terms of actually producing a BOSS image, this is some pop art from 1974 by Gerhard Richter, but it's very analogous to a BOSS background. So when you're trying to take a BOSS image, you take a picture of this speckle pattern. You then introduce a density gradient, so you run your wind tunnel. This will introduce an apparent displacement of this background pattern, which you then image. You take an image or a sequence of images. You then process these image pairs, so you track the displacements. You get a vector output in delta x and delta y, and then you can reconstruct a synthetic Schlieren image of what you've actually shown in your flow. So in a little bit more detail, those of you who've done PIV experiments might be familiar with the idea of cross-correlation. That's effectively what we're doing here. You're doing a PIV of Schlieren, if you think about it in those terms. So we obtain our images in native format, so we're trying to reduce any compression artifacts, because that will just make your images even noisier. We then process this using cross-correlation software. In this case, I've used Davis in strain solver mode, just because we're referencing the image sequence to one common background. We discretize this into small windows. We cross-correlate. The output is a vector field. So if you think about it, you're effectively sliding your reference with your flow image, and you get your delta x and your delta y. When we actually perform these tests on the HSST, so the flow direction in this case is vertically downwards. On the left-hand side, we have the background, which was laser printed and then back illuminated. And that's distance ZD, which is in the green arrow. On the other side, there is a commercial Nikon DSLR camera, which is focused on that background, and that's the distance ZA, which is in red. The distance between the two is ZB. Because this is a photographic technique, the important factors to think about is you're focusing on the background, but your model's in the middle. So there's going to be an apparent blur. And there is always a trade-off between where you place your camera, so that's this ZA distance, and where you place your background relative to each other. If you have them equidistant, you maximize your displacements you can track, but then your image becomes increasingly blurry. So it's always a trade-off. So in terms of what I'm presenting here today, I've done it in the sort of best for photography position, which is around 0.7. This is a sample BOSS image that was obtained for the testing the other week. Well, not the other week, but in June time. You can see that there is a very good representation or a very good capturing of all of the same shock features that were seen in the conventional Schlieren image. The Schlieren image that I showed you at the start of the presentation has a vertical knife edge, so that's a horizontal displacement. The image here, this BOSS image, is again horizontal displacements which have been tracked. The scale, so the intensity scale can be set by the user, so you can already choose, you can tune your image to what displacements you want to pick up. Before I started to look at the impact of things like the free stream density, I performed a processing study to work out which is the best algorithmic approach to track out these displacements. So I took a series of different windowing sizes. So I started with 5 pixels. You can see we've got good capturing of the sharp, so the shock discontinuities through the cone shock, the conical shock. I then doubled through a series. So this is now effectively 10 pixels, 20, 40. And you can see from 40, so the jump from 20 to 40, there is already the smearing or the blurring effect is starting to take over. And this only increases as you go to 80, then 100, then 200. You can sort of see some things there, but it's kind of like looking through a bathroom window at something, so there's not really much definition. Based on the results of this, the reason that you sort of want to have very small windows is you want to capture these very sharp, strong shock discontinuities. But that comes at the cost of capturing random noise in the free stream. So as in everything in life, there is a bit of a trade-off to play with. So small windows, better shock capturing, but high free stream noise. Larger windows, you get low free stream noise, but your shock capturing is poor. So there is a trade-off required. So in this case, I took 19 pixels. And what I've now done is I've applied that processing to the same background, but with 3 different cases of density. So this is 0.1 kilograms per meter cubed. This is around half. And this is around a third. So you can see there was already a weakening of the shock features and a consequent reduction in the displacements produced by the shock. Again, so there's a roughly sort of like a thirding from as the free stream value goes down by a value of a third, so too does the displacement around the shock. So in conclusion, for Schlieren, and in case of the vertical cut of Schlieren, our output is physically defined, so we have to do multiple runs, or we have to have more optics to capture different kinds of things. So if we want to do simultaneous Schlieren shadowgraph, you have beam splitters, already more complication. Our sensitivity is inversely proportional to our dynamic range. So if we want to make it more sensitive, we have to increase knife edge. We get ultimately infinitely sensitive, but there's no dynamic range, so what's the point? We can have high spatial resolution, but for BOSS, the power is in the processing. So for one single BOSS run, we can get magnitude or pinhole BOSS, horizontal cutoff, and vertical cutoff. So the 2 images directly above each other are equivalent in BOSS and in Schlieren. There is a trade-off between noise and shock capture, as I discussed in the processing study. There is comparable spatial resolution, at least in this arrangement. It's also very good for limited optical access, so if you want to have multiple views of the same model, you can arrange it within your wind tunnel test section, so you don't have to do multiple runs in different configurations. And there's a rough, at least in this case study, 3 times lower shock displacement, 3 times lower density. And on that note, I'd like to close with any questions. Thank you. Yeah.
Can you add a line for your non-artificial Schlieren to that pixel smearing? So you have the images there as well.
Yeah.
So what would that look like?
So, which, if I go back.
So back where you're showing the sensitivity to pixel count in your cross-correlation window size.
Yeah.
Irrigation windows.
This one.
Yeah. How does that compare with, or what's your best sort of estimate or guess? Are you facing similar uncertainties in your Schlieren?
So I haven't fully delved into that. So the ultimate aim of this study is to be able to compare a non-dimensionalized pixel displacement intensity with optical Schlieren intensity and see where the, but this is kind of still in work for the paper I'm writing on this.
Okay, my name's Tom Rees. I'm from Imperial College, and I'm going to be talking about hypersonic flow around faceted shapes. So why do we care about hypersonic flow about faceted shapes? Let me show you a video. Hopefully, nope. You're not seeing a video. I was going to show you a video of the re-entry of the European Space Agency's automated transfer vehicle. And what you would have seen is the big glowing thing in the sky, and at a certain point it would explode. And after this explosion, there'd be many, many smaller fragments falling down to Earth.
So that's fine and everything, and if you have really small fragments, you're going fast enough at the highest altitudes that the heat transfer rate to your fragments is going to cause these fragments to burn up. It's not so for the larger fragments. If you have larger fragments, this is what you get, right? So this is something we're trying to avoid. You imagine if something like that fell down onto Manchester, it might make the news. So we're trying to reduce the casualty risk associated with re-entry events. In order to understand the casualty risk associated with re-entry events and reduce it, we should understand what's going on during a re-entry event for a satellite, right? So the beginning of the re-entry event is generally sort of around 120 kilometers. That's the point of no return. That's where you can't really get back into orbit. And then at about 100 kilometers, the solar panel is going to break off, and then 70 to 80 kilometers, what's going to happen is there's going to be a catastrophic fragmentation event. So what we want to do is we want to try and understand what happens in this region here, right? What causes this catastrophic fragmentation event? Because if we can get our satellite to fragment into many smaller pieces, it's less likely that any of them are going to hit the ground, right? So what's going on in this region? Around 80 kilometers, right? Well, first of all, our aerodynamic forces are very, very low. Why is that? Well, our density is quite low, even though we're going at many, many meters per second. So our density is so low that it's equivalent to moving at 60 meters per second at sea level, right? That our dynamic pressure is about the same as moving at 60 meters per second at sea level. So therefore, it's not insane to claim that maybe this fragmentation is largely driven by heat transfer to the body, right? So people who have experienced hypersonic aerodynamics will be thinking, well, there are millions of correlations for heat transfer rates to hypersonic shapes. And you're right, but most of these correlations were developed for shapes like this on the left, right? There's a nice round shape. It's axisymmetric, hasn't got any sharp edges, hasn't got any flat surfaces. This is something which you can find an analytical solution to the Navier-Stokes equations for. This is what a satellite looks like. So I'd argue that whatever correlations we have for this, we probably can't use for a shape that looks like this, right? We need new correlations to describe the heat transfer rate to a faceted shape. Right, how do we do this? Well, we'll start simple, right? We need to understand what the heat transfer rates are to simple faceted shapes. Cylinders, tubes, or hollow cylinders, and cuboids. And by cuboids, I include long things like that, and really short, fat things, quasi sort of flat plates. Previous work that's been done on this is fairly limited, as you can imagine. Most people are interested in this thing on the left. But in the 60s, people studied heat transfer rates to cylinders. And later in the 80s, even fewer people studied heat transfer rates to cuboids. So I'm going to talk a little bit about one of these papers, this by Matthews and Eves, which looked at the heat transfer rate to a cylinder. Right, so here you go, some real science. On the left here, we have heat transfer with a surface distance along the cylinder. So this is your stagnation point. This is your shoulder here, and then this is downstream. And same thing on the right here, we have pressure. And so we have our experimental results, and they all line up very nicely with our theory. That's great. However, here we have this weird sort of note here. Reynolds number effects in these regions, and there's data missing, shall we say. So this is what I'm interested in. What's going on here, right? If we can understand what's going on here, we might be able to better predict the heat transfer to the corners of these shapes. And also, not just to the corners, but the regions around these corners. This is about 2 radii long, this length here. That's a significant region of the shape. Right, so what is this Reynolds number effect? Well, Matthews and Eves give us a clue, right? This is a shadow graph image, and what we see, we have our cylinder, we have a nice bow shock in front of it, we have a very strong expansion around the windward corner, followed by a separation bubble, and then there is a separation shock and a retraction shock either side. Now, maybe some of you are thinking, well, it's a sharp corner, of course there's going to be a separation bubble, and yes, that's definitely true in the incompressible flow, but we have observed in hypersonic flows that we can have no separation bubble at a sharp corner, right? So at some point, there's going to be a flow condition where the separation bubble forms, and it will significantly affect the heat transfer rate to this region of our square. So this is what I want to investigate, right? So that might not exist. I did CFD simulations. I'm not going to talk about the solver. It's an implicit solver. Ask me about it later. But here, I want to talk a little bit about how I chose the conditions we simulated. So here, I've plotted 3 things. Knudsen number with altitude, Mach number with altitude, and Reynolds number with altitude for a typical re-entry flow. And so our Knudsen number is about 10 to the minus 3, so just sort of on that limit of moving into a transitional flow. Our Mach number is sort of 10 to 15, and our Reynolds number is on the order of a few thousand. So I have these conditions, but we also need to square this with what we can achieve in the Imperial College wind tunnel, right? So for those reasons, I chose these conditions. So 15 conditions, all at Mach 5, and we decided to vary the Reynolds number and see what the effect of the Reynolds number was. How do we validate this? Right, well, it's difficult. There's not been a lot of previous experimental work on this, but we can compare our stagnation point heat transfer to some theoretical models. So we compared it to Fay and Riddell, and everything was within 5%, so we're happy that our results are not completely insane. Right, let's talk about the results. So here are some numerical Schlieren images of a flow around the 2D square. I want you to look at, so this is low, intermediate, and high Reynolds numbers, and I want you to look at this high Reynolds number case. First of all, we see a strong expansion around the windward corner, a separation bubble, and then a separation and reattachment shock either side. So that looks pretty much like the cartoon we sketched earlier. However, at these lower Reynolds numbers, at Reynolds number 6,000, Reynolds number 60,000, there doesn't appear to be anything there. So somewhere here, there's some transition of the flow regime. So we can investigate this further by looking at the skin friction. So if we look at the skin friction here, we see that, okay, for the highest Reynolds number case, our skin friction along the top of the square is negative here. Okay, there's a separation bubble. But interestingly, we notice also at this intermediate Reynolds number, there is a small, small region of separation. So the separation, unsurprisingly, shows dependence on Reynolds number, right? It sort of asymptotes to a constant length as we increase our Reynolds number, so that's reassuring. That's something that has an analogy in the incompressible flow. So we can maybe predict our heat transfer rate to the shape, depending on the size of this separation bubble. So let's talk about heat transfer. I'm going to talk about the windward phase first really quickly. Basically, there doesn't seem to be much dependence on Reynolds number, and it seems to agree quite well with this correlation, which was developed in the 60s. So I don't think there's much to say there. Let's talk about the heat fluxes to the side faces, though. This is the interesting thing. So obviously, we see that there is a strong effect on the separation bubble. With the fully developed separation bubble, the heat transfer rate underneath it is an order of magnitude smaller than the region outside of the separated flow. And so this, I would argue, would play a significant role in heat transfer to the corner. So if we compare our results to models that are used currently to predict heat transfer rate to satellites undergoing an atmospheric reentry, a demise, one method that is used is this modified Lees method. Now, that's the expression, but ultimately what it says is that the heat transfer to this surface of the square should be 10% of the stagnation point heat flux. It's not. In fact, it doesn't capture any of the physics there. It's both sort of overpredicts by an order of magnitude in this region and then sort of underpredicts by 50% there. So say that one's probably not the greatest method to use. And people have developed other methods. Some people have treated this top surface as a flat plate and treated it with an Eckert reference temperature model, but it's not really what a flat plate heat transfer distribution looks like. Others have treated the heat transfer rate as a function of surface curvature. And again, I don't really think that's appropriate here. We have much more complex physics. And we really need to get this bit right. And the reason for that is satellites fail, not because things burn away, not because of ablation, but because they're glued together. The joints fail at the corners, right? The epoxy joints which hold the satellite together fail. And therefore, it's really important that we get this region correct, because that will give us the best indication of when this satellite might fall apart and fragment. Okay, conclusions. 1, hypersonic flow around the square as a function shows a strong dependence on Reynolds number. Good, we're happy with that. At Mach 5, a separation bubble starts to form at around Reynolds number 50,000. This separation bubble strongly affects the heat transfer rate to the satellite. And secondly, many existing demise models fail to model this behavior, right? We're not capturing this, and therefore our predictions of casualty risk on the ground are likely very wrong. Cool. Future plans, we're going to extend simulations to 3D cubes. We're going to validate it experimentally using infrared thermography in the Imperial College Supersonic Wind Tunnel, and then eventually I'd like to investigate the effect of Mach number on this regime and other passage shapes. Thank you. I'm sponsored by European Space Agency and Fluid Gravity Engineering. Thanks to them. Okay.
Time maybe for one very quick question.
You've looked at that constant angular attack.
Yeah, that's a big issue, of course. Satellites will tumble. But fortunately, they'll tend to have modes in which they like to tumble. So for a cylinder, it might be an end-on mode or a spinning mode. And so you can sort of build up an idea of how the heat transfer changes with the angle of attack, then you can sort of develop a model for the tumbling modes. But yeah, that's a difficult problem, yeah.
Good afternoon, everyone. My name is Girish Janki from the University of Southampton, and together with Professor Ganapati Subramani, we've been looking at how the internal geometry influences the way a synthetic jet actuator behaves. Why a synthetic jet actuator? Such devices hold long-term potential in delaying stall, controlling lift, or reducing skin friction. The ability to generate a train of vertical structures can effectively counter the amplitude modulation effects between large outer scale structures and smaller inner scale structures in a turbulent boundary layer, and this has been shown to lead to a reduction in skin friction. In most flow control applications, what is desired is a high momentum flux and high energy efficiency. And to achieve this, there's been various studies which have been carried out. Further, because of the bidirectional nature of a synthetic jet, it is also important to look at the internal geometry, and that's what we are going to look at in this study. So how does a synthetic jet actuator operate? The main components consist of an actuator, which in our case is a speaker, a cavity, and an orifice. Periodic oscillation of the diaphragm causes alternate blowing and suction strokes, which result in momentary discharge of slugs of fluid. At the orifice edges, what happens is flow separation occurs, and a vortex sheet is formed, which rolls into a vortex ring. And if the conditions are right, the vortex ring will pinch off from the edge of the orifice and will advect under its self-induced velocity. One of the characteristics of synthetic jet actuators is that it has zero net mass flux, because the mass of fluid which is ejected and ingested is the same. However, we have a net momentum flux, because blowing occurs in one direction only, whereas during the suction stroke, the fluid is ingested from all direction around the orifice. In this specific study, we look at high aspect ratio orifices. Ward-Smith defined the aspect ratio as the ratio of the length of the orifice neck and the orifice diameter, and found that for a value which is greater than 1.25, what happens during the suction stroke is that the flow separates at the orifice edges, and a free shear layer develops within the orifice neck. And further down the neck, a transition occurs, and the flow reattaches the wall. So a separation bubble becomes trapped in the wall of the orifice neck. And this leads to a problem which we call necking. So basically, necking is just a reduction in the orifice diameter. And this causes blockage of the flow during the blowing phase. So what we are trying to do is to alter the internal geometry of the orifice, and in that sense, we can find a solution to the problem caused by necking. So to do that, we define a novel concept, which we call the orifice lip ratio. So we can basically divide the orifice plate into two parts, and the lower part we call that the orifice lip plate. So we vary the diameter of the inner lip, and we define the ratio as basically the ratio of the diameter of the inner lip and the diameter of the orifice exit. So we end up with different test cases ranging from a lip ratio of 1, where both the inner lip diameter and the orifice exit diameter are the same, up to a lip ratio of 9. To do the experiment, we used constant temperature anemometry to measure the exit velocity at a height which was away from the near field region. And at the same time, we fitted the actuator with a pressure transducer to monitor the pressure variation within the cavity. After analyzing the data, we also did phase log PIV on some specific test cases. So if we look at the results, what we find is from the hot wire measurement, we can actually plot the exit velocity over a range of operating frequencies at a single amplitude. Here, the frequency has been normalized with the cavity resonance frequency, which was found from the pressure transducer data. It is important to note here that the variation in cavity resonance was less than 5% for all the different test cases. So we assume that cavity properties remain the same, irrespective of the lip ratio. If we change the lip ratio, what happens is we end up with an increase in velocity, up to a certain point, which we found was a lip ratio of 5, beyond which any increase in lip ratio does not really improve the performance of the actuator. So why does this happen? Why do we get such a trend? To investigate, to understand the behavior, we perform phase log PIV. So let's take, for example, the case where the frequency was 750 hertz at an amplitude of 20 volts. So we can clearly see there are two different flow phenomena which are occurring. So if we have a lip ratio of 1, what happens is instead of vortex pinch-off happening, we end up getting a free shear layer which is developing. So this can be due to a blockage of the flow or a stroke length. At this point, we are not really sure what goes on. Whereas if we have a lip ratio, we can clearly see the coherent vortical structures being formed and pinching of the orifice edges and adducting away. So if we look at phase log, at a phase average data, we can clearly see there's a difference in stroke length. So we can see for a lip ratio, we get a much higher stroke length than for a case where the lip ratio is 1. If we take the velocity profile across the span, we can see that we get an increase in velocity of up to 30%. So if we look at the energy spectra of the hot wire, we can clearly see that both cases have the same energy content. So it means we end up having a jet in both cases. However, we end up with these harmonics in the case of a lip ratio. The harmonics provide a good indication that we have coherent vortical structures in the flow. Another interesting thing to note is the decay rate. We end up having a much steeper decay rate at higher frequencies for a lip ratio of 1, whereas for a lip ratio of 9, the decay rate stays almost the same throughout. What's the theory behind such behavior? Führer performed a similar experiment where he used on low aspect ratio orifices, but he varied the shape of the cavity. We adopted the same strategy here. And instead of varying the shape of the cavity, we just vary the shape of the internal geometry of the orifice. So what happens is if we have a lip, we can provide enough space to accommodate the flow structures formed during the suction stroke. And this prevents necking from happening. And this leads to vortex pinch-off which occurs. Further, we believe that there's a sort of virtual error shaping effect which takes place. So during the blowing phase, the nozzle adopts a converging shape, and this accelerates the flow and contributes to a high exit velocity as we've observed. So what have we done in this study? So we introduced a novel concept which we call the orifice lip ratio. We found that for high aspect ratio orifices, an inner lip diameter dampens the effect of necking on the ejected fluid, and this leads to an improvement in the actuator performance, up to 30% in exit velocity. We also found that vortex pinch-off is dependent on the orifice lip ratio, although there exists a threshold for the optimum value of the lip ratio. Thank you.
I see you tried a step change between the diameters. Have you tried any other shapes like a conical difference, for example?
No, we've just tried this inner shape, but that's a good suggestion for future studies.
Which one would be better for drag reduction? For example, the other one, the I think fusion structure.
So what the actual use of synthetic actuators in flow control is because of the ability to create coherent structures in the flow. So by using a lip ratio, we can actually extend the range of operation of synthetic jet actuators. So at higher frequencies, we can create coherent structures in the flow. Because in terms of reduction of drag, what we want to do is to target the large outer scale structures in the turbulent boundary layer, and this actually can counter the amplitude modulation effect, which happens.